We want to introduce a new concept today, which is going to be essential to the way we deal with heat transfer and chemical reactions going forward. And this is the concept of enthalpy, which is abbreviated capital H. What we're going to see is that enthalpy is basically interchangeable with the heat flow that we've talked about previously, as long as a chemical reaction or a physical process, a phase change, like a solid melting into a liquid, occurs against constant pressure. So what we want to introduce here is just the concept of enthalpy, talk about how it's related to heat flow Q, and then we'll talk more about how enthalpy works and how we can use enthalpy values for specific chemical reactions to make predictions about whether a more complicated chemical reaction will be exothermic or endothermic, and how we can relate the heat exchanged in a chemical reaction to the energy of a chemical bond. So one thing that we've mentioned before, and we'll come back to this when we talk in chapter 9 about gases, but if you're talking about the total energy change associated with something happening, whether it's a physical change like an ice cube melting, or it is a chemical reaction like a natural gas being burned in air, there's two ways by which your system can exchange energy with its surroundings. It can transfer heat, and we abbreviate heat flow with the lowercase letter q, or it can do work. The system can expand and contract as it produces more moles or larger amounts of gas, or fewer molecules of gas. And work, which we briefly discussed before in this lecture series, is abbreviated with a lowercase letter w. But that's only two ways that any type of reaction or process can exchange energy with the universe around it. And so we can say then that the total energy change for anything happening, let's say it's natural gas being burned in air, the total energy change for that natural gas being burned in air is equal to the heat transferred plus the work done. And the work done can be related to the external pressure acting on the system and the amount that the volume of the system changes. So this is more commonly rephrased in physics as saying the energy change, delta E, is equal to the heat flow minus the external pressure acting on the system times the change in volume. The change from the positive to the negative sign here has to do with conventions associated with work and what it means to do negative work or what it means to do positive work in physics. So don't be thrown off by the sign change here. That's something you can ask me about, and I'll be happy to go through with you. We'll look at it in more detail next chapter when we talk about gases. If we rearrange this equation, we could add the pressure volume product to the other side, and then we get the heat exchanged is equal to the total energy plus the pressure volume product. And so what we have here, the bottom line is that we have a relatively straightforward mathematical relationship that shows how the heat absorbed or released by our system is equal to the total energy. The heat exchanged is equal to the change in energy in the system plus the pressure plus the product of the pressure acting on the system times the amount the system changes in volume when whatever's happening happens. And this turns out to be mathematically very powerful, and it relates to the idea of heat flow and energy of a system being a state function. It doesn't depend on how you get from point A to point B, just depends that you started at point A and ended at point B. What this means is if a chemical reaction occurs at a constant volume, it can't change volume, and delta V must equal 0. If my reaction occurs at a constant volume, can't expand or contract, the volume change has to be 0, and all of the energy change has to be released as heat. This is what you typically study when you're operating a chemical system that's contained in a bomb calorimeter. You don't let the system expand or contract, and all the energy that's within the system will be absorbed or released as heat. So this situation would only occur if a reaction is carried out in a closed container that had a constant volume. And for most of the chemical reactions that we run them in a beaker or a flask that's open to the atmosphere on a benchtop. And so a system like that can expand or contract. It's not run at constant volume. Instead, it's run against constant pressure. The pressure in the flask is equal to the external atmospheric pressure. And so in those cases where the system can expand or contract, the heat flow is not the total energy of the system. Instead, the energy of the system is still equal to the heat flow plus whatever work the system's doing. And in most chemical situations, we run reactions under these conditions where the system is free to expand and contract against an external pressure. So for most of our chemical reactions, they're not run at constant volume. There is a volume change acting against a constant pressure. So anytime you just run a reaction on the benchtop, you are running a chemical reaction at constant pressure, which is free to expand or contract. So it can still do work it can still do work to exchange energy. It can expand or contract, or it can exchange heat with its surroundings, absorbing or releasing heat. If you run a reaction at constant pressure, we give heat flow a special new name. We call it enthalpy, capital H. And so heat flow is now referred to specifically in our chemistry class no longer as heat flow Q, but heat of reaction or enthalpy change. And we can say that the enthalpy of the system is equal to the total energy plus the pressure times the volume. Or if we're interested in chemical reactions where we're more often interested in the change in the enthalpy between the reactants and the products, how much heat does the system absorb or release as the chemical reaction occurs, we talk about an enthalpy change, which we abbreviate delta H, where delta is, once again, our usual notation. Delta means difference between the final and initial conditions. So just like we use delta T in the calorimetry equation to describe the difference between final and initial temperature, here we're using delta H to describe the difference in enthalpy between the products and the reactants. So delta H becomes the enthalpy change, which is a replacement for Q, the heat flow into or out of the system. And so when we're talking about a chemical reaction or a physical process like an ice cube melting, now we're talking about a system that's changing against a constant pressure. And instead of talking about heat flow, we're just going to replace the heat flow Q with the enthalpy change delta H. And that's how the enthalpy change delta H will now be the framework that we use to talk about how a reaction gains or releases heat as it's happening. And so what we're going to start showing you are what we call thermochemical equations, where we have a balanced chemical equation, and next to it, we're going to list an enthalpy change, where we can actually say, based on a calorimetry experiment and a variety of calorimetry experiments that have been done in the past, how much heat this reaction actually absorbs or releases. So for instance, if we're burning a natural gas like methane in air, the balanced chemical equation is 1 mole of methane, CH4, in the gas phase, reacts with 2 moles of oxygen, O2, in the gas phase, to give us a mole of CO2, carbon dioxide, in the gas phase, and 2 moles of H2O in the gas phase. One of my phase labels blew up on me there. So they're all in the gas phase, and there's our balanced chemical equation. Based on calorimetry studies, we can say, under a typical set of conditions, how much heat this chemical reaction is going to release. And we can start cataloging the amount of heat gained or released by these chemical reactions, and we can list it as an enthalpy change next to the reaction. So for the burning of 1 mole of methane, this should release 802 kilojoules of heat. So our thermochemical equation says 1 mole of methane reacts with 2 moles of O2 to give us 1 mole of CO2 and 2 moles of H2O, all in the gas phase. And the enthalpy change delta H for this reaction is negative 802 kilojoules. Burning 1 mole of methane releases 802 kilojoules of heat out into the surroundings, out into the universe. And delta H obeys all the same conventions as Q. If you have a negative delta H, your reaction is releasing heat. If you have a positive delta H, your reaction is absorbing heat. So if our enthalpy change is negative, we would say the reaction is exothermic, heat is released. So nothing new to learn here compared to when we talked about the heat flow Q. We just have a new symbol for it that we're going to use when we're talking about chemical reactions. And that's really all we're going to do with enthalpy right now. If we're talking about a heat release or an amount of heat absorbed by a chemical reaction, we're going to refer to it now as an enthalpy change, delta H, not heat flow Q, but everything else will be the same. Negative delta H is an exothermic reaction. Heat is released by the reaction, which is the system, out into the universe.